So starting with part 5, we're going to do somewhat of an analysis on the functions that you're aware of and their basic properties. And when we talk about functions, we like to look at and identify the domain of a function and the range of the function. Simply put, the domain is all possible x values. So all possible x values. These are often referred to as inputs, which is why in function notation, x is the input, and then the output is the range or the y values. So the range is all possible y values. And that the y values, being the outputs of any function, would be the f of x. So that's your output. That's your answer. That's your y value. So let's talk about a couple tips for finding domains of functions. And really the question is, what would make the function undefined? So what would make the function undefined? Because the majority of functions that we deal with are polynomials, and the domain of a polynomial is all reals. So what happens if you have division and you have a denominator of 0? So we cannot divide by 0 of 0. This also happens when we have any trig function where we get 0 in the denominator. So think tangent, cotangent, secant, cosecant, where we have a function in the denominator. We have to worry about what would make that function undefined. Also, if we have even roots or surds, a negative under an even root. So that is like the fourth root of -3. We get undefined there because we get an imaginary answer. Same goes with a negative on the inside of a log. Because the log is the inverse of an exponential function. Other just good things to note, we'll see these over and over and over again. The domain of an exponential function is always all reals, and the domain of a polynomial is always all reals. Okay, so then tips for finding range. This goes to some basic properties. First off, if we have division or a rational function, what do we have to worry about here? So this is like f of x divided by g of x. We would get possible horizontal asymptotes. And there's three different cases that we have to worry about here, because when we have two functions divided by themselves, we could have horizontal asymptotes. So if we talk about n for the numerator and d for the denominator, here are the three situations that we would have. So the first off, if the numerator is greater than the denominator, we do not have horizontal asymptotes. And we will talk about this when we get to limits, because we actually define where these rules come from. The second one is if the numerator is degree, so n and d talk about the degree, I should be clear, degree of n or d. If the degrees are equal, then all we do is take the ratio of the coefficients. So for example, if we had 2x minus 3 over 4x plus 2, then the horizontal asymptote in this example, e.g., would be y equals 1/2, or 2 over 4. And the last bit is if the numerator is smaller than the denominator, we call those proper fractions, even in ratios, and we would have a horizontal asymptote of y equals 0. Things you should know, seen from last year, but we just need to get good at that. A couple other functions that you should know the range of it would be odd polynomials will always have a range of all reals. Otherwise, we need to look at the graph and graph it to identify what the range is. So let's look at a couple interesting cases here. So it says find the domain and the range of the function f of x is equal to 3x minus 1 divided by the square root of x squared plus x minus 2. Now, I want you to think about two things. First off, look in the denominator. This will give you the domain. If I have any division problem, we don't want to be on the bottom. So with a square root function, so let's say square roots cannot be negative. That's what we have above. So if we don't want them to be negative, then we have to say x squared plus x minus 2 is greater than 0. That gives us this inequality setup. And you all know how to factor this. We write x and x, numbers that multiply to 2 that add, negative 2 that add to positive 1. So we would have plus 2 and minus 1. We say that's greater than 0. We don't set each of those inequalities greater than 0. This is where we now jump to our number line. So I have negative 2 and I have positive 1. I know this is a parabola that opens up, so this is going to go positive, negative, positive. You could also test values to the left, in between, and to the right of each of these numbers. And we can see that we have where this is positive is to the left of negative 2 and to the right of positive 1. So our inequality that we could write for our domain, so I would say d x is less than negative 2 or x is greater than 1. If we were writing in set notation, which this is the one that I prefer more, negative 2. And then why do we use parentheses rather than brackets here is because we're dividing. And if we have 0 on the bottom, then it's undefined. Then we write union, parentheses, 1, comma, infinity. Either of those works. If we were talking about the range, let's just do that in a slightly different color. If we were looking for the range, what we want to see is what happens when x goes off to really large positive numbers or when x goes to really large negative numbers. And so that makes you look at this function again and ask yourself, what happens when we're plugging in really large numbers? So in the numerator, if you picked a number, let's say 1,000,000, 3 times 1,000,000 plus 1, that plus 1 doesn't really do much. Likewise, if you have 1,000,000 squared plus 1,000,000 minus 2, 1,000,000 squared plus 1,000,000, and then take away 2, those other terms don't really influence what we are looking at. So when the numbers get really big, f of x behaves like this function. It would look like 3x over the square root of x squared. Well, we talked about what the square root of x squared would be when we talked about absolute values. So this is what it behaves like. It looks like 3x over, well, the square root of x squared is the absolute value of x. Now, this gives us something to look at. As x approaches really large positive numbers, then the y values, or the function, will get closer to, if I plugged in 3 times a really positive number divided by 1 time, or the same positive number absolute value, that would go to positive 3. Likewise, as the x values go closer and closer to a large negative number, the numerator in this case would be negative and the denominator would be positive. So the y values would go to negative 3. And so we would write the range, if I grab this and make it slightly smaller, just so we can fit everything in here. The range here would be anything lower than negative 3. So we can say y is less than negative 3, or y is greater than 3. Same way, if we wanted to write that in set notation, we would have negative infinity to negative 3, union, which means or, 3 to infinity. Now, I'm going to put this graph up. So we're going to go to Desmos. And we're just going to see from our algebraic analysis if we were accurate. So for this is the first time we're using Desmos. I hit the division sign. I'll type in 3x plus 1, and then in the denominator, square root, x squared plus x minus 2. And we can see, even if we didn't know what that looked like to begin with, looking left to right, we have this gap. If I trace this graph going left to right, we are getting closer as the numbers get more negative to negative 3. And then in between, we're getting the x values are getting closer to negative 2. And then there's a big space in between. And then our next vertical asymptote, if you will, happens at positive 1. And then the y values are getting closer and closer to positive 3. So that's the analysis of looking at the graph for the domain and the range. What happens if we're looking at a piecewise function? So there's two ways to look at this secondary one. We have the function f of x is equal to the absolute value of x over x. And we want to show that this function, this piecewise function, are the same. So what we do is we take our graph and if I look at f of x, if I pick any positive number, anything that's not 0, I would have one number divided by itself. So let's just change the thickness of this writing utensil so it looks a little better. Let's change it to pink. If I plug in 0, I would have 0 over 0. And we do not know what that is in this class. But any number to the right of 0 would be positive 1. Likewise, I can't plug in 0 over 0, but if I plugged in any negative number, I would have a positive number divided by the negative version of that self. Note, if I'm looking at the domain of this function with these two inequalities, the one value that I can't be is 0, because I would have 0 in the denominator. If I'm looking at the range of this interesting function, there's only two values that it takes on. We would have either y is equal to positive 1 or y is equal to negative 1. That's all it is. So that's a brief analysis of looking at functions. Domain gives us what the function can be left to right. Range gives us what the function can be down to up. Now, once we know what the basic values you can use for a graph is, how do we move them up, down, left, or right, stretch them, shrink them? So we're just going to talk quickly about transformations, and that will be the end of this video. So with our transformations, if we want to do a vertical translation, a shift of a function up, then we are just adding or subtracting a value, let's call it c, on the outside of that function. So we call that a vertical shift c units. If we want to do a horizontal translation, we'd have y equals f of x plus c on the inside. Anything on the inside, that's moving the function left or right, and we always do the opposite of what that value is. So if it's x plus c, we would call this a horizontal shift negative c units. So anything that's on the inside, we do the opposite. Anything that's on the outside, we do the same. If we wanted to stretch or compress a function, that is called scaling, and we stick a constant in front. So a constant multiple. If k is greater than 1, then that is a vertical stretch. If k is a fraction, so if k is between 0 and 1, we call that a vertical compression. And do know, if k is a negative number, so if k is less than 0, which just means negative, then that just flips the function over the x-axis. If I wanted to compress or shrink a function, do a horizontal scaling, just like we said with translations, that would be multiplying by a constant on the inside as opposed to on the outside. So just like we said before, inside we do the opposite. So if the constant that we're multiplying by is greater than 1 on the inside, This is a horizontal compression. This is most obviously seen when we're dealing with trig functions because they're oscillating functions. And likewise, if k is a fraction, so it's between 0 and 1, that would be a horizontal stretch. And if k is less than 0, which just means that we're dealing with a negative value, that would be a flip over the y-axis. So both are very similar, just in opposite ways. So take, for example, the function y equals, or f of x equals x squared. We should know what the standard parabola looks like, but just in case, we're going to graph this function. That is the parent function. And we want to analyze these different translations. And this will look very similar to your homework. So I would like you to write down what each of them are, then graph. So this number on the outside would move our function up 2. Nothing else changes. We have our parabola just shifted up 2. If we have x minus 3, that is shifting our function to the right 3. 1, 2, 3. Everything else stays the same. The domain stays the same. The range stays the same. The range changed when we moved the function up 2. If I'm looking at this f of x minus 3, it's also the same thing as the function x minus 3 squared. Well, what happens if you plug in a negative number? So this should flip over the y-axis. But because x squared is an even function, even symmetrically, which means you are symmetric over the y-axis, plugging in a negative doesn't change our graph. It's because it's even. If it was an odd function, it would actually mirror what would happen if you just had a negative out front. And the last bit, if you had 4 in front, instead of going to 1, 1, like we would normally have, so I'm just going to put this in black, normal function would look like this. That 4 in front, that scalar, is making it grow 4 times as fast. So 1, 2, 3, 4. So this, if I plugged in 1, I get 4 out, or negative 1, I get 4 out, makes our function skinnier. What I like to say in class is, if I made you 4 times your height, but you stayed the exact same weight, what would happen to you? And most of you guys would realize that you would turn into a string bean. Likewise, if I said 1/2 your height, but everything else stayed the same, you would see that that'd be like me pressing down on the top of your head and compressing you. So we have some practice for the homework problems here in, I think, the 4th homework assignment of just shifting a function up, down, left, or right. It's very good practice for understanding the basic properties of functions. In the next video, we're going to talk about everything you need to know about logarithmic and exponential functions, and then we'll move into trig, and then we'll be closer and closer to being done with the review chapter. So see you in part 6.